Alright, in this part of the chapter we're going to be going over drawing the D or the L configurations of Fisher projections for common monosaccharides. And what you can see here is we're ultimately going to position these molecules in a way so that we can turn this sideways structure into something called a Hayworth. Hayworth. I can't spell. Projection. Hayworth projection, which is going to be our ring structure. So we have the open chain that we represent using Fisher projections, and then we'll have our ring or closed chain, our hemiacetal, as Hayworth projections. Okay, so just carrying on, Fisher projections are used to represent carbohydrates. It places the aldehyde group or the ketone group at the top. It's the most oxidized. It shows the H's and the OH's on the horizontal intersections on chiral carbons. And I guess I should point to that one too. And then achiral carbons are towards the bottom and are shown just as CH2OH's. Only the chiral carbons get the intersections. And then, of course, if it is on the left, it'll be L, and if it's on the right, in terms of the hydroxyl group, it'll be D. And so that's how we assign the L or the D isomer. It's the chiral carbon farthest from the carbonyl, and the OH group determines L or D. So here you have glucose. We're finally getting to the important monosaccharides, and there's 3 of them that we're going to look at in this chapter, but we'll take a look at glucose real fast. So glucose, you can see here, the isomer of glucose that we're focusing on for this example is the mirror image. But remember, at every chiral carbon, we could have a difference. For example, at carbon number 4, we could have the OH group be over here. That would still leave everything else in the molecule as a mirror image, but it would not be a mirror image with what we have here. So those are still isomers, but those would be diastereomers, and they wouldn't be called glucose. Mirror images, we can give the same name, and then we can just designate if it's the L or the D. And the molecule that I'm referencing at the moment, the one where if we switched carbon number 4, you'll see in a minute that's actually galactose. So the sugars are named for basically how they're different on those chiral carbons, but then I'm talking about common names, but then L or D will designate which one we're looking at. So these are the most important monosaccharides. We've got D-glucose, D-galactose, and D-fructose. You can see they're all hexoses. 2 are aldoses, one's a ketose. They all have the same formula, therefore they're all isomers. D, D, D. Our bodies like the D sugars. Now, glucose and galactose are different on carbon number 4. It's just as I was sort of saying before. Carbon number 4 has a flipped OH group. Otherwise, glucose and galactose are identical. And then fructose is also similar to glucose in carbons 3 through 6, where it's different from glucose's carbons 1 and 2. It being a ketose, the carbonyl group is on carbon number 2 instead of carbon number 1. So that is how these are different. This is also easy to flip. We can turn fructose into glucose, and I'll talk about that in a little bit. So D-glucose, most common hexose, found in fruits and veggies, corn syrup, honey, dextrose in our bodies, as we call it when it's in our blood. And it's the building block of many disaccharides, 3 of which we're going to take a look at: sucrose, lactose, and maltose to some extent, and then polysaccharides. We'll take a look at those too. Now galactose, this was the milk sugar. It's a disaccharide, it's found in the disaccharide lactose, which is the milk sugar, but galactose is what we'll find in milk. And it's important in our bodies because it's involved in cellular membranes, in the brain and nervous system, meaning it helps to conduct the nerve pulses, the action potentials, the signals that our brain sends. Fructose. Fructose is a ketohexose, obviously same formula, it's an isomer. It's part of the disaccharide sucrose, which is table sugar. Fructose on its own is actually sweeter than sucrose, the disaccharide. And we can obtain fructose by just hydrolyzing sucrose. In fact, there's a process involved in the making of high fructose corn syrup where an enzyme does that breaking down, the hydrolysis part, to yield more fructose because fructose is sweeter. So it's really just a high fructose corn syrup is just a sugar solution, a table sugar solution where more of the fructose is available to hit our tongues. All right, so a quick learning check. Identify the following sugar, this is ribulose, as being D or L. So again, if you're starting this from scratch, you identify the most oxidized carbon, you make sure that's at the top. You look for the farthest carbonyl carbon from that would be carbon number 4. And then you determine if the OH is on the left or the right. And here it's on the right, so D, ribulose. Now, there are conditions associated with the amount of glucose that we have in our blood and the ability to maintain normal levels. Glucose would have a normal level in the body around 70 to 90 milligrams per deciliter. And having too much or too little means you could fall into different categories of condition. And we have glucose tolerance tests that measure blood glucose for several hours after you ingest glucose to see first, what it does when it enters the bloodstream, how long it stays there, and if you can level out. So let's talk about these two conditions real quick. So diabetes can cause hyperglycemia. Hyperglycemia is when you have too much sugar in your blood. This happens when the pancreas is unable or insufficiently making insulin. Insulin is the molecule that goes and tells your cells that glucose is around and that they should start pulling in glucose into the cells. So if you don't have enough glucose or enough insulin, then the glucose stays in your blood for too long. And so your levels go up really high, like 350 milligrams high per deciliter. Symptoms of this could be excessive thirst and urination, increased appetite and weight loss, and even in older people this can lead to excessive weight gain. On the flip side of that, you can be hypoglycemic. This is when the blood glucose levels rise and then they decrease so rapidly that they get as low as 40 milligrams per deciliter. Low blood sugar can occur as a result of the overproduction of insulin. It can cause dizziness, general weakness, muscle tremors. Sometimes even a diet that consists of several small meals, high in protein and low in carbohydrates, can yield hypoglycemia. You can burn through your we call it glycogen. We'll talk about glycogen in a few slides. That's how we store our sugar. We can burn through our glycogen stores in one day if we don't continue to eat, if we're fasting, let's say. And once that happens, you start to break down fat and muscle because our bodies can actually break those down and convert them into glucose to run our bodies, because that's what we run on. We run on glucose. So quick learning check. This is a Fisher projection. Identify this as a D or L isomer. That should have been easy by now. We've done this a few times. That was the L isomer. Don't exactly know which sugar this is, but we'll talk about that. Well, we don't have to name random sugars like this. You could test yourself and ask if this is an aldose or a ketose, and what kind of sugar is that? Is it a tetrose, a pentose, a hexose? This is an aldotetrose, by the way. All right, Haworth structures. So Haworth structures are the most stable form of the pentose and hexose sugars. So rings in nature tend to need to have at least 5 members to be stable. 4-member rings and 3-membered rings are particularly unstable. Haworth structures are produced from the reaction of the carbonyl group and a hydroxyl group in the same molecule. We know from the last chapter that an aldehyde or a ketone can react with an alcohol to form a hemiacetal. Now we can, I'm going to draw sugar here, 2, 3, 4, 5, 6. Here's our aldehyde. We've got an OH and an H, an OH and an H, an OH and an H. That's carbon what, number 4? Here's our H, OH, and then we have I guess this is just a CH3 or CH2OH. Okay, so here's our sugar. The alcohol group now that's going to react with our carbonyl is just the alcohol on carbon number 5. And so we know that a hemiacetal forms when an alcohol and an aldehyde react. So this is going to cause a new bond to form a linkage between carbon number 5 through an oxygen to carbon number 1. That's what's going to happen. So carbon number 5 here, carbon number 1 here. Carbon number 1 used to be the aldehyde. Carbon number 5 has the alcohol group on it. They're going to form the hemiacetal, and we're going to get a ring structure that's more stable. Now the way that we draw these Haworth structures, I think I called it a Haworth projection earlier. I apologize for that. Haworth structure, Fisher projection. I think I got them mixed up. So we've got the Fisher projection here. In this case, it's D-glucose. And then we want to turn it into a Haworth structure. So the first thing we do is we want to flip this clockwise 90 degrees. And we keep the orientation of the H's and OH's in the same orientation. We don't want to flip anything. Like this OH on carbon number 3, since it's on the left here, needs to be on the top here, just like we're tipping it over. All right, so that's the first thing that we do. Then we want to fold the horizontal carbon chain into a hexagon and bond the O from carbon 5 to carbon 1. So carbons 2 and 3 form the base. Carbons 2 and 3 form the base. And it helps if you know what the ring structure is going to look like. It's got carbons 2 and 3 on the bottom. Carbons 1 and 4 are up. Carbon 5 is there. This is an oxygen. And then carbon 6 is also still present. It's just up, and we usually show that with the CH2OH. So this is the ring structure we're going for. Now on every one of these corners, we have 2 more things that are on our ring. And here is where keeping these guys on the bottom and these guys on the top is important. I'm going to now put the hydrogen and oxygen, or hydrogen and hydroxyl from carbon number 2 onto this molecule. So H is up and OH is down. Carbon number 3, OH is up, H is down. Carbon number 4, OH is down, H is up. Now when we get to the carbonyl carbon, we are going to start calling this guy the anomeric carbon, because there's going to be 2 different forms that this can take, similar to the L and D, though we're not talking about L and D anymore. Once it's in the Haworth structure, we typically already know which sugar we've done that with, D-glucose. So let me show you what happens next. When this structure folds and you bend everything and you connect them all, we have to now actually form the hemiacetal bond. So remember, carbon number 1 that had the carbonyl, this one is going to gain a bond to an O and then be left with a hydroxyl on it. So that's what's happening here. The bond to the O happens, and now carbon number 1 has a hydroxyl group. Now the hydroxyl group, just depending on which direction this is facing, whether it was CH that way or CH this way, we're going to end up with either the OH on the downside of this ring or the OH on the upside of this ring. If you were looking at the ring flat on, everything would look like it's either on top or below the ring. When it's on the bottom, we call it the alpha isomer. When it's on the top, we call it the beta isomer. So once it forms a ring, we have to now designate whether we have alpha D-glucose or beta D-glucose. And you're going to see here in a second that it really doesn't matter which one you draw, as long as you name it properly. So there's no right or wrong answer when you're drawing Haworth structures. You have to pick a position for the hydroxyl on your anomeric carbon. So just know how to name it. When you draw it down, the OH down, you call it alpha. When you draw the OH up, you call it beta. This is important for when bonds happen, okay? Let's say glucose here is going to form a bond to another glucose. Well, if alpha D-glucose forms a bond to another glucose, we'll have our sugar, and that OH is down, so it's going to form a bond that looks something like this to the other sugar. The down position here is going to indicate that this is an alpha, let's say 1,4 bond, from carbon number 1 to carbon number 4 of the next sugar. But if the beta anomer is the one that does the reaction, and the OH was up, then that might look something like this. This would be a beta 1,4 bond, because it was beta from carbon number 1 to that same carbon number 4. And again, on a sugar where the OH is down, like this, on the next the next sugar, if they were all glucoses, OH would be down, and so that's why I'm drawing these two bonds from carbon number 4, so I'm drawing them down. I guess I could. This one's down, and this one's down. If this was galactose, the OH is actually up here on the top, and so that bond might look something like that for the sugars, right? But this would still be a beta 1,4 bond because of the orientation of that hydroxyl group, and because we're dealing with either alpha or beta glucose. So we need to pay attention to that kind of stuff. Now, when you're drawing them, it doesn't matter which way you draw it. You can see the cyclic structure here for both of them, beta and alpha. Now, 64% over here means that when in any solution, we're going to find about 64% of the closed structures as betas. And there's a reason for that. The alpha isomer has what we call steric hindrance. There's two OH groups that are bulky, both right next to each other on the bottom of this ring. There are electrons here in these O's that are going to repel each other a little bit. So this is slightly less stable than the situation over here, where our hydroxyl groups are on opposite sides of the ring. Everything's sort of staggered. Nothing is in each other's way. So the beta form is a little more stable. Now, what happens in water is that this is constantly being hydrolyzed. The hemiacetal bond is always being broken and then reformed, broken and reformed. And so in any mixture of, or any solution of a sugar, we're going to have something called mutarotation, where the alpha isomer will suddenly open into a straight chain, or back into its open chain, and then it'll close again, and it can turn back into a beta or back into an alpha. But it'll, so this is indicating that it can open but also go back into alpha. It can also open and turn into beta. So that's what we're talking about here. So there's a flipping back and forth of these positions. Now, whatever position it happens to be in when it forms a bond is going to be determined by other things too, the steric hindrance of the neighboring molecule that it's bonding to, and that sort of thing. If it's a linkage that's formed by an enzyme, then it's going to be a specific, the enzyme will specifically grab beta instead of alpha. That sort of stuff can happen, but because the OH can be up or down, when they form a linkage, we need to designate whether that is an up or down linkage. Now, just to show you, that was glucose. Here's galactose. When galactose closes, it also forms an alpha or a beta. And here, the difference between this structure and glucose is that the OH on the carbon number 4 is up, where in glucose it was down. Here's glucose again. See, carbon number 4, it's down. So you have down, up, down on your hydroxyls, whereas in galactose it's down, up, up. And then here is fructose. Fructose is our 5-membered ring. This one happens because the alcohol group on carbon number 5 reacts with carbon number 2 instead of carbon number 1. So we get this form of a ring. Still, pay attention to that 3 and 4 now make the base or the bottom of our ring instead of 2 and 3. And that the CH2OH groups can be on opposite sides of each other, but it still is the position of the OH that determines alpha and beta. So OH down is alpha, OH up is beta. All right, so real quick, draw the cyclic form of D-galactose. Try not to just go back and look at it. And if you want to make it more challenging, draw alpha D-galactose. But that, or beta, doesn't matter. So just give that a shot. Now, it should, again, flip it on its side, make sure to keep the orientation of those groups. Connect them, or start to turn them into the ring, even if you haven't connected it yet. But again, keeping track of where those groups are. And then link it and name it properly. If the OH is down, it's alpha. OH is up, beta. All right, I'm going to go ahead and stop this video. Hope it records, and do part 3 in a moment.